Groups provide the mathematical axiomatization of the notion of symmetry. Let us begin with the definition of a group. A group G is a set with a distinguished element E called identity. A binary operation of multiplication that we denote x times y, and a unary operation of inversion that we denote as x inverse, satisfying the following axioms. So 1. For all x, y, and z in the group, x times y times z is equal to x times y times z. So this is the associative law. 2. For all x in G, x times identity and identity times x is equal to x. So this is the axiom of identity. And 3. For all x in G, x times x inverse and x inverse times x is equal to identity. If we take any symmetric object, then the set of symmetry transformations of this object will necessarily form a group. Well, indeed, let us consider this icosahedron. So here we can consider transformations of icosahedron that preserve this overall shape. For example, this rotation moves the points of the icosahedron but preserves its overall shape. Let us take a symmetric object and consider all possible symmetry transformations of this object. Then the associative law is the general law for the composition of transformations. So if we take any three functions and compose them, then the associative law will universally hold. And because of that, associative law holds for compositions of symmetries of transformations. For any object, we have a trivial symmetry, so which we call identity transformation. So this is a lazy transformation that does nothing. So it takes the object and doesn't move. If our object is completely non-symmetric, then identity transformation is the only symmetry of this object. On the set of symmetries of an object, there is a binary operation, which is composition of symmetry transformations. So if we take two symmetry transformations, so this one and then followed by this one, then the composition of these two symmetry transformations is again a symmetry transformation. So this means that on this set of symmetries of an object, we have a natural binary multiplication operation. And we also have inversion. So any symmetry transformation can be undone. So if we transform the object like this, and this is a symmetry transformation, then the inverse transformation is also going to be a symmetry transformation. And all three axioms of a group will automatically hold for the set of symmetry transformations of any object. Be that a geometric object, any mathematical structure like a differential equation, or an object from nature. Because the notion of symmetry is fundamental in nature and mathematics, so these simple axioms of a group lead to a rich and beautiful theory. We point out that symmetry is also a cornerstone of modern physics. When we develop a new physics theory, be that relativity theory or the standard model for elementary particles, the first thing that we postulate is the kind of symmetry that this theory will possess. I presume that you had already taken the first course on group theory, and today we're going to go deeper by looking at actions of groups on sets. In this framework, a set will be a symmetric object, and the group will be its set of symmetry transformations. Definition. An action of a group G on a set M is a map rho from G cross M to M, and the notation that we will use is rho of G acting on M. This will be an element from M. So here G is an element of the group and M is an element of the set. Satisfying two properties. One, rho of E is the identity on M, and two, for all G and H in G, rho of G times H acting on M is equal to rho of G acting on rho of H acting on M. Our first proposition is that rho can be viewed as a group homomorphism from the group G to the group of symmetries of the set M, where this sim M is the set of invertible functions f from M to M. Well, invertible is equivalent to bijective. And our claim is that rho is a group homomorphism. Let us give a proof. From the second axiom of the group action, we have that rho of G composed with the rho of G inverse is the same as rho of G times G inverse, which is rho of identity. And from the first property, we know that this is identity on M. And a similar calculation shows that the same is true for the composition in the opposite order, rho of G inverse times rho of G. From here, we conclude that rho of G is an invertible function from M to M, and thus belongs to the group sim M of permutations of the set M. Now, the claim that this is a group homomorphism is immediate. So indeed, we have rho of G dot H is equal to rho of G composition with rho of H. So this holds by the second property of the group action. Then rho of identity is equal to identity element in the set of sim M. And this calculation shows us that rho of G inverse is the inverse of rho of G. So the compositions rho of G inverse and rho of G are inverses of each other in this group. This establishes the fact that rho is a group homomorphism. Next, let us give examples of group actions. In our first example, let's take as a group the group GLNR. So these are n by n invertible matrices. And as a set, let us take Rn. Then we have an operation where we take a matrix and a vector and associate to it a new vector. So this is matrix vector multiplication. In this example, we take as an underlying object a vector space, and then consider what is the group of symmetry transformations of a vector space. These will be invertible transformations of a vector space that preserve the vector space structure. And we know that such symmetry transformations are invertible linear transformations. Any linear transformation may be represented by a matrix, and we have this operation of multiplication of a matrix by a vector. And then we conclude that the group of symmetries of vector space Rn is the set of n by n invertible matrices. A beautiful and powerful idea is to apply group actions for the study of groups themselves. Let us see how we can make groups act on groups. Our second example is the action of a group G on itself. So this means that as M we take G by left shifts. Here the action of an element G on an element A will be just the product, G times A. So here G and A are elements of the group. In these notations, A is viewed as an element of M and G is viewed as an element of G. We can easily verify the axioms of the group action here. So we need to show that rho of E is identity transformation on the group G. So this follows from the fact that rho of E acting on A is E times A is A and is equal to A. And the second property, so to check that rho of GH acting on A is equal to rho of G acting on rho of H A. So here the left hand side is G times H times A, and the right hand side is G times H times A. And we see that the equality holds because of the associative law axiom of a group. For the left shifts, we will also use the notation LG acting on A. So instead of rho of G, we'll write LG. We can also define the right shift action. So of the group on itself. However, when we define the right shift action of RG acting on A, we have to be a little bit more careful, and this action is defined as A times G inverse. Let us see, why do we need to put inverse in this formula? So what we need to verify is that the right shift by the product GH is equal to the composition of a right shift by G and a right shift by H. Let us compute what is right shift by GH acting on element A. By our definition, this is A times GH inverse. And the inverse of GH is equal to H inverse times G inverse. Now, if we calculate right shift by G times right shift by H acting on A, so this will be right shift by G acting on A H inverse. And this is equal to A H inverse times G inverse. And we see that both expressions give us the same answer. If we didn't have the inverse, then we will not be able to flip these two elements and the action will not work. We can combine these two examples together and define the action of G on itself by conjugation. So here, when we conjugate with an element G and act on element A, so this is defined as G times A times G inverse. And I leave it as an exercise for you to verify that this defines the action of a group on a set. We can generalize this construction by making G act not on elements of itself, but on other structures associated with the group, like subgroups. For our next example, so let us take a group and let H be its subgroup. consider the set M of left cosets of H and G. Then we have an action of G on M by left shifts, where LG acting on a coset AH is equal to the coset of GA times H. Next, let M be the set of all subgroups in G. Then we have the conjugation action of G on the set of subgroups, where if we have CG acting on a subgroup H, so this will be the conjugation of the subgroup GH, G inverse. And we know that CG, the conjugation, is an automorphism of the group. And because of this, so the conjugate of a subgroup is a subgroup. We give the following definition. Suppose a group G acts on a set M, and we fix an element M in this set. The orbit of element M under the action of group G, so this is denoted as O of M, is the set of all elements rho of G acting on M as G runs over G. For example, if we look at the action of G on itself by conjugation, then the orbit of an element A is the set of all expressions GA, G inverse as G runs over the group. And so we see that this is a conjugacy class of A. So here, under this action, orbits are conjugacy classes. If we take the example when the group G is the group of rotations of a plane, and the set M is R2, then the orbits will be circles around the origin. Let us prove the following lemma. Two orbits either do not intersect or coincide. So let us give a proof. Suppose the orbits of M1 and M2 intersect. So suppose this intersection is non-empty. This implies that there exist elements G1 and G2 in the group such that rho of G1 acting on M1 is equal to rho of G2 acting on M2. Consider an element in the orbit of the first element. So this will be rho of G acting on M1. This can be written as rho of G times G1 inverse times rho of G1 acting on M1. But rho of G1 acting on M1 is the same as rho of G2 acting on M2. So what we get is we get rho of G times G1 inverse acting on rho of G2 M2. And by properties of the group action, so this is the same as rho of G times G1 inverse times G2 acting on M2. And we see that the result belongs to the orbit of M2. So this tells us that every element in the orbit of M1 actually sits in the orbit of M2. And by symmetry, we have the converse claim that orbit of M2 sits inside orbit of M1. And we conclude that if two orbits have a non-empty intersection, then this implies that these two orbits are actually equal. And this completes the proof of this lemma. As a corollary, we get that M is a disjoint union of orbits. So that is, orbits partition the set M. And so this can be illustrated in this example. So if we consider concentric circles on a plane, so these are orbits under the group of rotations of R2, then we see that distinct orbits do not intersect, and the whole plane is partitioned as a union of disjoint concentric circles. Our next definition is the following, that we say that G acts on M transitively if M consists of a single orbit. So that is, for all M1 and M2 in M, there exists an element of the group G such that rho of G acting on M1 is equal to M2. So this means that we can transform any element of the set to any other element of the set using the group action. As an example, consider this tetrahedron. So we take G to be the group of symmetries of this tetrahedron. And as a set, we take the set of vertices. So we have 4 vertices in a tetrahedron. And we can see that by applying symmetries, we can move any vertex to any other vertex. So here, the group of symmetries of the tetrahedron acts transitively on the set of vertices. In addition to the action of the group of symmetries on the set of vertices, we can also look at the action on the set of edges. And again, here we will have a transitive action. By applying symmetries, we can see that we can move any edge to any other edge. And finally, there is the action on the set of faces of a tetrahedron. And yet again, the action on the set of faces is transitive. So if G is the group of symmetries of a tetrahedron, then we get 3 actions. So one is the action on the set of vertices. Then second action on the set of edges. And the third action on the set of faces. And all of these actions are transitive. Let us list regular polyhedra in 3-dimensional space. So we have a tetrahedron, we have a cube, we have an octahedron, we have an dodecahedron, and finally we have icosahedron. So these are called Platonic solids. Let us ask a natural question. How can we define a higher dimensional generalization of these objects? So it turns out that this question is quite subtle. Well, first we introduce the notion of a simplex. So that is, we put a finite number of points in n-dimensional space. Then we join some of these points with edges. Then we create two-dimensional faces where some set of edges will form a boundary of a two-dimensional face. Then we create three-dimensional faces where some two-dimensional faces will form boundaries of three-dimensional faces, and so on. Of course, not every simplex will give us a regular n-dimensional polyhedron. It turns out that to define which n-dimensional polyhedra are regular, we need to invoke the idea of transitive actions. First, we define the notion of a flag in an n-dimensional polyhedron. A flag in an n-dimensional polyhedron is a sequence of a vertex, an edge, a two-dimensional face, a three-dimensional face, and so on up to n-1 dimensional face, all attached to each other. For example, for this octahedron, a flag will be a vertex, an edge that's leaving this vertex, and a face that contains this edge in its boundary. And we see that there are many different flags in this octahedron. So now we can give a definition that an n-dimensional polyhedron is called regular if its group of symmetries acts transitively on the set of flags. In particular, this would imply that the group of symmetries will act transitively on the set of vertices, on the set of edges, on the set of faces, and so on. But this property is actually stronger than just transitivity on each of these sets. It also says that all these objects are attached to each other in the same way. Disappointingly, when we go to higher dimensional spaces, we do not acquire new regular polyhedra. In each higher dimension, we will have an n-dimensional generalization of a tetrahedron, a generalization of a cube, and a generalization of an octahedron. And beyond three-dimensional space, no new regular polyhedra will emerge. Our next definition is the definition of a stabilizer. A stabilizer of an element M in the set M is the following set. Its stabilizer of M is the set of all elements G in G such that rho of G acting on M is equal to M. So these are all elements of G that do not move the given element. For example, if we consider the group of symmetries of icosahedron and consider its action on the set of vertices, then all these rotations will be in the stabilizer of this vertex. Proposition A. Stabilizer of M is a subgroup in G. And B. If M1 and M2 belong to the same orbit, then stabilizer of M1 and the stabilizer of M2 are conjugate to each other. And in particular, this means that they will have the same size. So more specifically, that if M2 is rho of G acting on M1, then stabilizer of M2 is equal to G times stabilizer of M1 times G inverse. So let us give a proof. For part A, we need to show that we have a subgroup. So this means three things: that identity element belongs to the stabilizer. The second thing to check if G and H belong to stabilizer of M, then G times H also belongs to the stabilizer of M. And the final property of a subgroup is that if G belongs to stabilizer of M, we need to verify that G inverse also belongs to the stabilizer of M. Let us prove this. So by the property of the action, rho of E acting on M is equal to M, because this is identity transformation on this set. From here, we conclude that E belongs to the stabilizer of M. And this verifies the first property. Then if we assume that G and H belong to stabilizer of M and look at the action of GH on M, then we will get rho of G acting on rho of H on M. Because H belongs to the stabilizer, rho of H acting on M is equal to M. So we get rho of G acting on M. And because G belongs to the stabilizer, this is equal to M. And this will imply that the product G times H belongs to the stabilizer of M. Finally, for the last property, so we assume that G belongs to the stabilizer of M, and we need to prove that G inverse belongs to the stabilizer of M. So let's consider rho of G inverse acting on M. So we need to show that this is equal to M. But G belongs to the stabilizer of M. So this tells us that M is equal to rho of G acting on M. But then by axioms of the action, so that's the same as rho of G inverse times G acting on M, so which is rho of identity acting on M, which is M. And so this proves that if G belongs to the stabilizer of M, then G inverse belongs to the stabilizer of M. And we verified all these three properties of a subgroup. To prove part B, we need to show equality of these two sets. So we need to show that G times stabilizer of M1 times G inverse sits inside stabilizer of M2, and that we also have the opposite inclusion. Suppose H belongs to the stabilizer of M1. So we need to show that G times H times G inverse belongs to the stabilizer of M2. So let's verify this. So we have rho acting on GH, G inverse acting on M2. Now this equals rho of G times rho of H times rho of G inverse times M2. Well, we have that M2 is equal to rho of G acting on M1. If we apply to both sides rho of G inverse, we'll conclude that rho of G inverse acting on M2 is equal to M1. So here this becomes rho of G times rho of H acting on M1. But H belongs to the stabilizer of M1. So rho of H acting on M1 is just M1. And we get rho of G acting on M1, but rho of G acting on M1 is M2. And this proves that this element belongs to the stabilizer of M2. So we have verified this inclusion, and the opposite inclusion I left for you as an exercise. Now we come to the main theorem of this lecture that connects the notions of the orbit and the stabilizer. Theorem: let G be a finite group acting on a set M, and let M be an element of this set. Then the order of the group is equal to the size of the orbit of M times the order of the stabilizer of M. As a corollary, we get that the length of the orbit of an element M is a divisor of the order of the group. To prove this theorem, we are going to show that there exists a one-to-one correspondence between left cosets of the stabilizer subgroup and the points in the orbit of M. And this correspondence works in the following way. So if we take the left coset G times stabilizer of M, then it will correspond to the point rho of G acting on M. And so this is a point in the orbit of M. We need to prove three things. So one, that this correspondence is well defined. Two, that is injective. And three, that it is surjective. Now, what does it mean that this correspondence is well defined? Well, so here the left coset is not determined by a single element. So it could have that the left coset with element G is equal to the left coset of the stabilizer with element H. And we need to show that the answer in the right-hand side does not depend on the choice of the representative. So this means that we need to show that rho of G acting on M is equal to rho of H acting on M. So how do we prove this? So the equality of these cosets means that H belongs to the coset G times stabilizer of M. And this tells us that H is equal to G times S, where S belongs to the stabilizer of M. Then what is rho of H acting on M? So this is equal to rho of GS acting on M, so which is rho of G times rho of S acting on M. But S is an element of the stabilizer, so this is rho of G acting on M. And then we show that this equality holds. Rho of G acting on M is the same as rho of H acting on M. So this proves that this correspondence, where left cosets are mapped to points in the orbit, this correspondence is well defined. The claim of injectivity of this correspondence is actually the converse of our previous claim. So we need to show that if rho of G acting on M is the same as rho of H acting on M, then these two left cosets are the same. So if we assume that rho of G acting on M is equal to rho of H acting on M, and apply rho of G inverse to both sides, so this will tell us that M is equal to rho of G inverse, rho of H M. And this tells us that G inverse times H belongs to the stabilizer of M. Then H may be written as G times G inverse times H. And then we see that this element belongs to the coset G times stabilizer of M. because G inverse H is in the stabilizer. And if H belongs to this coset, this tells us that these two cosets are actually equal. So the coset of G is equal to the coset of H. And this gives us injectivity. If the images of G and H are the same under this correspondence, then the preimages are also equal. And finally, surjectivity is obvious, because if we have a point in the orbit of M, then it can be written as rho of G acting on M. And then it has a preimage which is G times stabilizer of M. So all three properties will hold. Since we established this one-to-one correspondence between the points on the orbit and the left cosets of the stabilizer, we conclude that the size of the orbit of M is equal to the number of left cosets of the stabilizer of M, which is the index of the subgroup stabilizer of M in the group G. And then the claim of the theorem follows from Lagrange's theorem, that the order of the group is equal to the order of the subgroup times its index, or the number of left cosets. As an example, let us consider conjugation action of a group G on itself. So here we said that the orbit of an element A is the same as a conjugacy class of A. So what is the stabilizer of an element A? So this is the set of all elements G in the group such that CG acting on A is equal to A. So this condition can be expressed as GA G inverse is equal to A, or this is also equivalent as GA is equal to AG. So if we multiply on the right by G both sides. And so this can be expressed as a set of elements G in G that commute with the element A. And this subgroup is denoted Z of A and is called centralizer of A. So this theorem tells us two things. That first of all, that the size of the conjugacy class of A is a divisor of the order of G and is equal to the order of G divided by the order of the centralizer of A. As a next example, so let us consider the group G to be Sn, the group of permutations of numbers from 1 to n, and let M be the set of k element subsets in the set 1, 2, 3 up to n. Because G permutes elements in the large set, this group will also act on the set of k element subsets here. And it's easy to see that this action is transitive. For any k element subset here, there is a permutation of the whole set that will map this k element subset to the subset 1, 2, 3 up to k. So this means that we have a single orbit in this action. Let us choose a specific k element subset, 1, 2, 3 up to k. So what is the stabilizer of this element? So these will be permutations of a big set that preserve this subset. But then it's clear that they will also preserve the complement of this subset. And we see that the stabilizer of this set will be a direct product of the permutation group of k element sets and a permutation group of its complement, n minus k. And then we conclude that the number of k element subsets in the set 1, 2, n is the orbit, or the size of the orbit of m of this element, right? So because of the transitive action, we have a single orbit. And the size of this orbit is equal to the order of the group divided by the order of the stabilizer. And since the order of the permutation group is n factorial, then we get the formula n factorial over k factorial times n minus k factorial. And this gives us a well-known result in combinatorics, that in a set of n elements, the number of k element subsets is this binomial coefficient. Finally, let us use this theorem to compute orders of symmetry groups of regular polyhedra. We have 5 regular polyhedra in 3-dimensional space. And with each of them, we associate the following combinatorial data. So we can count the number of vertices, the number of edges, and the number of faces. The names of the polyhedra come from the number of faces. So octahedron has 8 faces, and dodeca is 12, so dodecahedron has 12 faces. We see that there is also a numerical duality here. So for cube and octahedron, so we have the number of edges is the same, but number of vertices and faces will switch. And the same phenomenon will happen for the pair dodecahedron and icosahedron. This numerical duality is actually explained by geometry. So here, if we mark the middles of all faces of an octahedron, then as a result we will get a cube inscribed in the octahedron. And if we do the same procedure for a cube, then we will get a smaller octahedron which will be inscribed in the cube. The same will be true for an icosahedron and a dodecahedron. As a result, dual polyhedra will get the same symmetry group. So because the set of symmetries of this octahedron will be the same as the set of symmetries of an inscribed cube. This duality may be also applied to a tetrahedron, but it turns out that a tetrahedron is self-dual. If we take middle points of faces of a tetrahedron and join them together, then we will get a smaller tetrahedron. So although we have 5 different polyhedra in 3-dimensional space, we only have 3 symmetry groups. One for a tetrahedron, one for the pair octahedron and cube, and one for icosahedron and a dodecahedron. When we talk about symmetries of regular polyhedra, there are actually 2 groups that we can consider. One group is the group of rotations of this polyhedra. So we consider only symmetries that can be obtained as rotations. But then there is also a slightly larger group where we are allowed also to use mirror symmetries. So for example, this tetrahedron will have a mirror symmetry with respect to this plane, and then this will be also a symmetry transformation of a tetrahedron. Let us compute the order of this larger group. So this means that we include both rotations and also mirror symmetries. Let us compute the order of the symmetry group for the tetrahedron. So we consider action on the set of vertices. And we mentioned that this action is transitive. So this means that there is a single orbit, and the length of the orbit is the number of vertices. So that is 4. Now, let us compute the order of the stabilizer of a single vertex. So if we look at the vertex, then we see that in its stabilizer we have 3 rotations by angles 0, 120, and 240 degrees. And we also have 3 mirror symmetries that through planes that pass through this vertex and one of the edges. So we see that the stabilizer of a vertex is isomorphic to the dihedral group D3. So its order is equal to 6, and we get that the order of the group of symmetries of a tetrahedron is 24. We could have chosen a different action for this calculation. So for example, if we look at the action on the set of edges, then the length of the orbit, So again, this action is transitive, and we have 6 edges. So we have 6 edges in this orbit. Now let us look at the stabilizer of this edge. We can have a mirror symmetry with a plane that passes through this edge. And we can also have another mirror symmetry through the opposite edge that will be perpendicular to this one. And so what we see is that the stabilizer of an edge is isomorphic to Z2 cross Z2, because these two mirror symmetries will commute. And we will arrive to the same answer. So the length of the orbit here is 6, and the order of the stabilizer is 4. Let us look at the octahedron now and consider the action on the set of vertices. For the octahedron, we have 6 vertices. And if we look at the stabilizer of the vertex, then we see that the stabilizer of a vertex is the group D4. So we have 4 rotations that will preserve this vertex. And we also have 4 reflections. So we get that the number of vertices, which is the length of the orbit, is equal to 6. And the stabilizer of a vertex is isomorphic to D4 and thus has order 8. And we get that the order of the symmetry group is 6 times 8, which is 48. And finally, for the icosahedron, so what we have is the number of vertices is equal to 12, and the stabilizer of a vertex is isomorphic to D5. So here we see this pentagon here, and we have 5 rotational symmetries around this vertex, and we have 5 reflections. So what we get is that for icosahedron, we have a transitive action on the set of vertices, and there are 12 vertices, and the stabilizer of a vertex is isomorphic to D5, and with order 10. And so the order of the symmetry group is 12 times 10, which is 120. So we conclude that there are 120 symmetry transformations of icosahedron.